Hey, uh, welcome back to Cyber Lab. Hope y'all's midterm season is going okay. And daylight savings didn't hit y'all too hard. Just note that at Cyber we will be on a little bit of a skeleton crew since a bunch of our offices are actually currently in New York, I believe, competing for a CTF competition. So yeah, bear with us. Starting with some announcements. So our quarterly Cybercross AI Symposium has been scheduled. It will be on Tuesday during week 10 in 6 to 8 p.m. in Long Auditorium. This is where you get a chance to present your projects you're doing here in Cyber Lab. You can see all the other projects that are being done in like ACM AI. You can see some of the other things. For example, ECTF might present. Like PBR will have a couple presentations of some cool challenges that were solved. It's a lot of fun. Come show up. We do need to collect an RSVP due to like budget restrictions and whatnot with the university. So please RSVP. And since you're in CyberLab, we do expect that you do present your project at Symposium. If you can't make it, please make sure to let your lab lead know. We do understand that this is on Tuesday and not, Wednesday when CyberLab is held. So just putting that. But yeah, scan this QR code. This is also posted in Discord. Yeah, and we do provide food, so it should be fun. Cool. All right. So some more quick announcements. This Saturday, we will be playing Buckeye CTF. So join us for lunch at 11 a.m. at the Nev Crosswalk if you'd like to get lunch on the hill together. And then we'll walk over to the engineering 4 Tesla room to play Buckeye CTF together. Should be a lot of fun. Everybody is invited. No prior experience required. You don't have to have already done CTF. So Buckeye is usually a pretty beginner-friendly CTF. Our malware defense course. So this is like the malware cyber lab here, but significantly more thorough and with just a lot more time, right? We have 10 weeks in the quarters and 3 hours a week. So you get to do a lot more cool things. If you're interested in taking this course, it is held Thursdays, 12 to 3 p.m. during winter quarter. You can enroll in your class planner or at this link. And yeah, it should be fun. Currently, there are no enrollment restrictions, so you should not need a PTE to enroll. So we are potentially going to be doing a competition known as CCDC. If you've ever done Cyber Patriots, this is like the college version of that. If you are interested, scan this QR code or go to that link and fill it out. If there's enough interest, we might try and compete in CCDC this year. Just note that this will be a decent time commitment due to the training and the preparation that needs to be done, as well as the actual competition itself. Cool. Okay, and then lastly, we have some upcoming socials. So in 2 weeks, we will be having our quarterly cyber potluck. A lot of fun. Show up, come grill and chill with us at a grill in the university apartments. Please RSVP at that link, just so that we know roughly how many people will show up. You don't have to bring food if you don't want to. We cover the cost of all the meats and whatnot. So if you want to bring snacks, you're more than welcome to, but we do not expect anybody to. We will also, the week after that, on Friday, have our quarterly Cybercross ICPC Sawtell trip. But this time, we're inviting a couple other committees, notably AI and Cloud, to also join us. So if you're interested in having some fun, potentially getting some exercise running to Sawtell, it's around 2.5 miles, and it's mostly downhill or flat. Or if you want to bus over there, either option is totally acceptable and normal. Save the date. RSVP will be coming out soon to collect numbers. But yeah, 8 p.m. on Friday, November 21st. And then just one other thing, after cyber, all cyber academies and labs, we generally just like hang out right outside the room if you're interested on coming to the hill together to have dinner. So yeah, without further ado, I guess I'll get into my presentation about the recent AWS outage. So just quick agenda. I'll go over like the event itself and then jump into a background of what AWS is if you've never heard of it, talk about what actually failed initially, the resulting cascading failures, as well as the resolution. And I do want to note that most of the information from this presentation about this specific incident comes from this link, which you can read up. It's very dense, which is why I wanted to make this presentation to hopefully make it more digestible, but there's a lot of interesting technical detail in there that I would highly recommend checking out. So yeah, it's just another day at UCLA, 11:58 p.m., trying to submit your assignment to, at 11:59 p.m. Totally normal UCLA behavior. And you open Brew and Learn and it's not going to load. What gives? Reddit has to chime in, right? Yeah. We crashed Brew and Learn by procrastinating, right? No. It's actually a lot of different sites went down, not just Brew and Learn. Some big names like Snapchat, Duolingo, Fortnite, Lyft, Reddit, Slack, and a lot more websites are having issues loading their pages and doing things. So normally you think, right, it's UCLA Wi-Fi, right? No, it was actually AWS. So before we jump into it, what is AWS? So AWS is known as a cloud compute provider. What this is you can kind of compare it to in the old days, or UCLA actually does this right now. You want to run a website. You buy some hardware, you put it in your own location, you connect it to the internet, and you have what's called on-premises compute. You run, like, people connect to your website by connecting to your machines that you physically own in your own data centers to visit the website. Cloud computing is the idea that let's consolidate all of these machines into a single location where this company is responsible for managing the hardware, and you simply rent a small portion of this in order to be more cost effective, both on a scale of, set a scale of size, right? This cloud computing provider will handle billions of dollars worth of infrastructure, as well as, right, you pay as you go. You only pay for the amount of resources you use. And AWS is the largest in the world. I just grabbed some statistics here. It has 30% of the global share market of cloud infrastructure and had $100 billion of revenue in 2024. And it's used by many companies, including all the companies mentioned on the previous slide. So before we jump into what actually happened, just very, very basics. What does the cloud actually offer? Well, first one is storage, right? The cloud will offer you the ability to store data in the cloud. This can be disk storages, like if you have a virtual machine, you have a virtual disk. You could have databases. So this is like SQL, key value, caching databases, etc. You can also, and there are also some what I might call cloud native storage, which doesn't really exist in like a standard computing environment, but exists in the cloud. For example, buckets, which you can kind of think as like a key value store, but for files. We also have compute. So this is things that actually calculate things or run programs, right? You have your virtual machines. You just have a Linux server or a Windows server running in the cloud somewhere that you're just given the IP address and the password or key to connect to it. And you can do whatever you want with it. We also have container execution. So maybe you have a Docker container, if you know what that is, and you just want to run it in the cloud and you don't want to worry about managing the operating system. There are a lot of opportunities and services to execute containers. And then you can even go all the way down to like code execution. I don't want to manage this container. I just want to give some Python code and just have it run. I don't want to like set up the Python environment. And the cloud has that as well through things known as like functions or lambdas. And then lastly, networking, right? Storage and compute, that's all great, but if you can't connect to it, kind of useless. So this involves a lot of connecting the storage and compute and the greater internet to each other. And there are a lot of different things that go into play here, right? Premium internet connections, standard internet connections, VPNs. Maybe your company's large enough, you want a physical direct connection to AWS. All of that comes into play with networking. Oh, and by the way, if anybody has any questions, just feel free to raise your hand, even if it's on something that was like 3 slides ago. So what exactly went wrong? So the root of all of AWS is this service known as DynamoDB. It's essentially a distributed, so runs across many different servers. Highly available means even if like 1 or 2 servers goes down, maybe a data center got hit by a hurricane, the whole system should still be able to manage requests to this database. Key value document storage, so similar to MongoDB if you've ever used that. It's fast, efficient, horizontally scalable, which means you can just spin up more machines part of the same database for higher reliability and maybe speed. And it's used both externally by a lot of customers. You can go to AWS's website and say, hey, I want a DynamoDB instance running for whatever app. But AWS also uses this internally for their other services. So how do you access this database? Well, you first need to contact DNS. DNS being the method that translates what we call like domains, so like dynamodb.aws.com, for example, into an actual IP address you can use to contact. So let's say you have your client and you want to access DynamoDB. You ask AWS's DNS servers, where can I access the database? AWS's DNS will say you access it at 10.2.3.4, at which point you just go to that IP address to make whatever operations you need on the database and get the response, right? All fun and games and pretty simple, right? Well, couple complications. First one, we have many different endpoints, right? If we want to make this globally redundant, we need to make sure that if one of these if one of our backend servers that we're redirecting traffic to goes down or breaks, we need to have backups or failovers for those automatically. So the DNS server will need to be able to provide multiple different endpoints, not only for redundancy, but also, right, one server can't handle all gazillion gigabytes of data that's being sent to AWS all at once. So DNS has to keep track of multiple endpoints. And then on top of that, your DNS server itself is distributed, not only within AWS, but just across the globe, right? You have Google's DNS servers, you have Cloudflare's DNS servers. All of these will have a copy of these DNS endpoints. And even within AWS, right? Every AWS region, so like their North America servers, their European servers, they will need a copy of this DNS in order to prevent, let's say I'm in Europe and I want to connect to a North American database. I would rather get the IP address of the North American server from a local server before sending the data across the ocean, rather than asking the server across the ocean for the IP address, getting the response, and then finally making the request over to North America. So what happens if a server needs to be added or removed? Well, that's where the issue kind of started to reveal itself, right? Well, how do we do that? Idea one, let's just have a single program, check for availability, and if a server goes down or needs to be added or removed, you just update the DNS everywhere. Any issues with this? Yeah, so the issue here is it's just a single point of failure, right? What if your program that checks availability goes down? Maybe it's in a data center that just went, lost power or overheated. Well, then you're screwed. So this is not going to work out. So let's run this program, but on multiple machines around the world. Every single one of them just constantly checks all of the DNS servers, right? Are they online? Sorry, check all of the DynamoDB servers. Are they online? And then update the DNS entries across the world as appropriate. Here, however, we run into race conditions, right? The program in North America might see 3 servers in North America are online and nothing in Europe is online. But the European server, for some reason, is able to see the European servers online, but not the North American servers. And all of a sudden, you have 2 different programs having 2 different ideas of what the DNS record should look like, which is not great. They're going to fight of each other for whichever one is correct to update it. So they'll fight for whatever the resulting state of the DNS server is. So that's where we get closer to what AWS does. You have one distributed program plan what this final state would be, and you have another distributed plan actually enact those changes. The planner, as they call it, it's just distributed, just looks for it looks at what's available and saves the plan onto a distributed file system, which is then picked up by the distributed program that enacts the changes, or the enactor. However, just one minor issue, right? How do you determine which planners plan to use, especially if there are multiple planners running at a time? And the answer to that is use distributed versioning, which, if you want to learn more, take the distributed systems class. I love that class. I would highly recommend it. So yeah, this is essentially what AWS uses. Are there any questions? Was that kind of clear? All right, cool. So, and then one last thing I do want to mention is this thing known as talk to issues, right? Or time of check and time of use. So this is also known as a race condition, right? Let's say I have some program. It needs to make some check, like maybe my bank account balance is above 0, and then it acts on that information, right? If my balance is positive, let me withdraw money. But if you have multiple programs trying to run at the same time, running the same code, one program will check and say, hey, balance is above 0. The other program might check and say, hey, balance is above 0. And then both of them may try to withdraw money. But because of this difference between the time of check versus the time of the use of that information, you can end up where maybe both of these withdraw the money from my bank account below $0 when that wasn't supposed to happen. And this can happen in the real world, especially in distributed systems, due to things like latency or network delays, right? Sending data from here to Europe fundamentally can't go faster than the speed of light. And usually you're looking at least like 100 millisecond delay. So yeah, very simple replication of issue. This is essentially what the enactor code looks like. It gets the plan, checks to make sure the plan that it got is the latest, applies them to all servers, and then it removes the plans from the DNS servers that are old. So they had one planner, just get the plan. Let's say it's version 5. It then checked to see if the plan is the latest version, in which case, yes, it is. And then it goes ahead and applies the plan to all servers. But for whatever reason, this planner, which, by the way, this is what actually happened. This planner got stuck and just took a while. In the meantime, right, the planners had generated a bunch of new plans. So let's just say we're now in version 10. Maybe it's an hour or two later, and another enactor starts running on a different server somewhere in the world. It gets the latest plan, version 10, checks the plan was the latest, which yes, it is. So then it goes ahead and applies it to all servers. So it updates our DNS version, the server data served on our DNS to version 10. And our DNS server actually will have a copy of both 5 and 10. Don't worry too much about this. And let's say at this point, it just freezes up, or maybe it's trying to apply to other DNS servers. At the same time, our first program goes, time to apply my plan to this server. Well, it just reset that version to an older version from 10 to 5, which, depending on how much you might know about networking, this isn't actually the worst thing in the world. It just means that your DNS is slightly outdated, so it might contain outdated, outdated information. But in this kind of distributed system environment, outdated is still much better than broken. You just might occasionally have a failure, but it should more or less work. The real issue was down here. Remove old plans less than 1 hour old. This planner said, oh, version 5, that's over an hour old. So it went ahead and deleted version 5 from the DNS servers, and all of a sudden, the DNS record is empty and chaos. No DNS, no contact. Nothing can contact any DynamoDB server in US East 1. And yeah, this is fine. Everything's okay. So DynamoDB is down. What next? Well, DynamoDB, which you can think of as our storage, is down. What about compute and networking? Well, turns out they all depend on DynamoDB. So starting with virtual machines, right? The system looks at all of the physical servers available at AWS and says, I only want to spawn or attempt to spawn virtual machines on healthy servers, right? Ones that I'm able to contact and verify they're working and not like in a weird state where maybe the disk failed, for example. So existing virtual machines are fine, right? They're not subject to this health check. However, when DynamoDB goes down, because of its dependence on it, the virtual machine creation system sees all of AWS's servers as unhealthy. So no new virtual machines can be created. Even after DynamoDB recovers, due to the mass number of failed checks, new attempts to essentially do this health check keep timing out. So the virtual machine creation system keeps seeing almost all of AWS's servers as unhealthy, which essentially creates an issue where systems just cannot scale up anywhere. So this is both for, I want to spin up a virtual machine as an external customer, but other AWS services, which will come into play later, can't spin up compute services for them to run stuff on as well. We also had issues with the compute networking. Once they fixed the issue with creating virtual machines, then they had the issue of connecting, applying the configurations required in order to connect the network to the virtual machine. And this system that did this network configuration got bogged down with way too many requests with the backlog, and it started getting really slow, with the result that some virtual machines would be created, but they wouldn't be fully connected. Where the VM is there, it's reporting as healthy, but from some regions you can connect to it, but from some other regions you just can't due to this delay, essentially creating an inconsistent ability to connect to these virtual machines. Okay, so our compute is on fire, right? That's great. What about our networking? So outside of virtual machines. Before we jump into it, just want to quickly go over what a network load balancer is. Essentially what this does is it's like a front-facing thing or server that takes in requests from a bunch of different sources and spreads it between a bunch of backend servers. And this can be very useful for both load balancing, right? Balancing the load between the backend servers, or if any of the servers goes down or you need to add servers, it's very easy to just redirect traffic as necessary, as long as the load balancer is aware of the status of the backend servers. So because of that, right, the load balancers, however, also are distributed, right? AWS has a lot of these load balancers for various different applications. What happened was, since new machines to run load balancing spawned without a connection, the network load balancer manager tried to spawn new network load balancers and saw that they were unhealthy or cannot be connected to. However, sometimes they would make a health check and it would be healthy. what this ended up is this cycle where it would essentially see that it's unhealthy, try and delete the machine and recreate it, and then it sometimes becomes healthy, so it starts sending traffic to it, and then it sees it's unhealthy and it tries to delete it, and you just end up with this huge amount of creation and deletion of virtual machines and changes to the DNS. And the result was just there wasn't enough capacity, which led to the whole network load balancing, which is fundamental to a lot of cloud systems, just failing, and you couldn't connect to stuff. Because of these three failures, right? We had compute fail, storage, we had fundamental compute failure with the virtual machines, storage fundamentals with DynamoDB failing, and the network just failing, right? A lot of other AWS services just got impacted. Of note, some of them include no Lambda execution, so that code in the cloud. There's this thing called Amazon Connect I never heard of, but some companies use it for like voice and texting for like customer service issues. Because DynamoDB went down, there were periods of time where you actually just could not log into the AWS console to make any changes, which is not great. The AWS Support Center, for example, also went down. So you couldn't go in and complain to AWS that your services were down, just normal stuff. And almost everything relies on these kind of services. So essentially all of AWS in US East 1 was down. So yeah, just like rough timeline, there's a lot of text on the page, but I'll just like go over quickly. The first DynamoDB issue started around 11:50 p.m. on the 19th. So the engineers got on it and they find the issue. Takes them almost 3 hours, which is not great, but they eventually managed to try and get it to recover around 2:25 a.m. At this point, right, virtual machine creation is now starting, but it fails to do so due to the reasons I talked about earlier. Around 2:32, DynamoDB itself is fully recovered, but we'll see that a lot of other services were still down because of this, right? Virtual machine creation finally recovers at around 5:30 a.m., but they had to put in a rate limit to prevent how quickly virtual machines could get spun up due to like a massive backlog of attempts to spin up new virtual machines during this time. And because the virtual machine creation starts working at that point, but it has networking issues, that's when network load balancing starts having issues, right? It creates virtual machines, can't connect to it, and now all of a sudden network load balancing is stuck in the infinite loop of crashing and recreating. So around 6 a.m., you started seeing like severe networking issues with virtual machines. And at 9:30 a.m., they said, screw it, and disabled health checking on the network load balancer in order to get it to stabilize. And finally, eventually around 10:30 a.m., when y'all are waking up, by the way, these are all in Pacific time, so where we are located here, around 10:30 a.m., the virtual machine network connectivity was restored, so new virtual machines would come up being able to connect to them. And they finally fully went through the backlog of all the virtual machines that needed to be created around 1:50 p.m. And then at 2 p.m., they finally made the last change needed to get back to a healthy as normal state at 2 p.m. If you're curious, Brew and Learn, after they noticed like these issues, they just put a static "we're having issues" pages, and I don't think they removed it until like 3. But that was technically like roughly an hour after they could have done it. Cool. Are there any questions about the timeline? I know that was a lot of information, but yeah. Yeah. Yep. Yes, it was always been there. And it just happened to take down the largest region that everything else depended on. Yeah, or like if you remember from earlier when I said like you have the planner and executor or the enactor, the enactors usually like run really fast. They just tell all of the places, just run it. So generally there wasn't a window of opportunity for a race condition to happen. And there were like some checks in there, right? If it tries to apply to a DNS thing and it's not as it expected, or like some other DNS enactors also editing that record at the same time, it would like back off and try again. And there were other like version checks, but this very specific combination just happened to happen that day after one of the planners or enactors got stuck for a while. Yeah, good question. Cool. So before we wrap up, just some like lessons learned, right? Developing and managing these resilient, gigantic distributed systems is hard. There's a lot of work that goes into making sure they stay online. And despite your best efforts, the whole thing can just come crashing down just based on one small little thing you've overlooked. AWS is US East 1, which is the region that was affected by this outage, which is the only one, by the way, that got directly affected by the outage. If you tried to create virtual machines in other regions, it was fine. It still took down a ton of different companies. Some companies like Reddit, for example, like they had some issues initially, but they were able to move a lot of that traffic to other regions and then were able to operate fine once they got that initial period of rollover. But also just kind of speaks to the centralization of the internet, right? Everything is dependent on AWS's capability to keep this region online and bug free. Not even just AWS, DynamoDB in US East 1, right? So just a thought, right? The internet was supposed to be distributed. All of a sudden, it's not. And then, yeah, lastly, like cloud companies are vulnerable to outages just as much as any other organization. You might think of these as like these really large behemoths that won't fail or crash, but they do make mistakes sometimes, like this. And then, I got there's like some comments online like, yeah, Amazon's been going on like massive layoffs and firing sprees. They probably laid off the person who knew how to fix this. So another comment. So yeah, are there any questions? All right, cool. Let's go ahead and break up into our normal groups. So we'll have AdBlock Lab in the back, we'll have Malware Lab here in the front, and we'll go down the hall for Fuzzing Lab.